Welcome dear students. In this lecture we are going to talk about the structure of the benzene. Benzene is the parent nucleus of the aromatic hydrocarbons and it was discovered in 1825 by Michael Faraday. After its discovery, then its molecular formula was determined using elemental analysis and some other techniques, and the molecular formula of the benzene comes out to be C6H6, which shows that it has 6 hydrogen atoms with the 6 carbon atoms and the carbon to hydrogen ratio that is very low. This low carbon to hydrogen ratio is an indication that the benzene is unsaturated. Now comparing the benzene with corresponding alkene and alkynes, in alkene with 6 carbon there are 12 hydrogen, in alkynes with 6 carbon there are 10 hydrogen atoms. So comparing the benzene with corresponding alkene and alkyne shows that benzene has even lower carbon to hydrogen ratio as compared to the alkenes and alkynes, which concludes that benzene is much more unsaturated as compared to the aliphatic hydrocarbons that are alkenes and alkynes. So its molecular formula shows it is unsaturated, and comparing with alkene and alkyne it shows that benzene is much more unsaturated as compared to corresponding alkenes and alkynes. After the discovery of the benzene, when its molecular formula was determined, now the next challenge was to determine the structure of the benzene, and in that perspective, the first concept that was discussed, it was the possibility of the straight chain structure of the benzene. My dear students, the straight chain or open chain aliphatic hydrocarbons, they prefer addition reactions. They discharge the reddish brown color of the bromine water. They discharge the purple color of the acidic or alkaline chamenophore, and they also show hydration reaction when they are treated with water in the presence of some mineral acid. But on the contrary, benzene prefers substitution reaction. Benzene does not discharge the color of the bromine water or chamenophore, and benzene shows no hydration reaction on treatment with water. It means that benzene does not show any of the characteristic feature of the open chain or straight chain aliphatic unsaturated hydrocarbons. So the possibility of the straight chain structure of the benzene is ruled out, as it does not show any characteristic feature of the open chain unsaturated hydrocarbons. The next was, if it is not an open chain structure, then it might be a cyclic structure. When benzene was treated with the bromine in the presence of iron bromide, it formed only single monosubstituted product, and that was the bromobenzene, and no other isomeric form was produced. And it was possible only if the benzene is cyclic in nature, because if there are 6 carbon atoms which are attached in the straight chain fashion, then my dear students, there must be at least 3 monosubstituted products, one with the carbon number 1, second with carbon number 2, and third with carbon number 3. But benzene shows only one monosubstituted product with no isomeric form. It means the straight chain structure is ruled out and the cyclic structure is confirmed, because it is only possible if the 6 carbon atoms are joined in a cyclic fashion, then the possibility of a single monosubstituted product can be seen. Otherwise, in the straight chain fashion, it can never show a single monosubstituted product. So this reaction confirmed the cyclic structure of the benzene, and when the benzene was hydrogenated, it formed cyclohexane, and my dear students, 3 hydrogen molecules were added per benzene molecule. One hydrogen molecule is added if there is 1 pi bond, and if the 3 hydrogen molecules are added in any unsaturated compound, it means that unsaturated compound has 3 pi bonds. So this bromination confirmed the cyclic structure, and the hydrogenation confirmed the presence of the 3 pi bonds in the benzene. Keeping in view these 2 points, then in 1865, Auguste Kekulé presented the first cyclic structure of the benzene, in which the carbons are joined in a hexagonal fashion with alternate double bonds. My dear students, when this Kekulé structure was presented, which is usually written in this form, then there were some objections on the Kekulé structures. Like, the first objection was that according to this structure, benzene is unsaturated, so it should prefer the addition reactions. Then why benzene prefers the substitution reactions? This why cannot be answered by the Kekulé structure. So it was its first objection. The second objection was that if there are double and single bonds in the benzene, the single bonds are longer bonds with a bond length 1.54 angstrom, and the double bonds are the shorter bonds with the bond length 1.34 angstrom. It means that all the bond lengths in benzene, they are not equal, and if all the bond lengths in the benzene are not equal, then benzene cannot be a regular hexagonal, and if it is not regular hexagonal, then it must produce the 6 monosubstituted products. But we know that benzene gives only one monosubstituted product. Why it gives only one monosubstituted product if all the bond lengths are not same? This question was not answered by Auguste Kekulé. Then the third objection was that when the benzene should be brominated, it should form two ortho products, because in one ortho products the two bromine atoms should be joined to those carbon atoms that have double bond, and in the other ortho product the two bromine atoms should be joined with those carbon atoms that have single bond. So there should be two ortho products of the benzene, but it shows only one ortho product. These two ortho products are different, but in actual benzene shows only one disubstituted ortho product. Why is it so? This question was answered by the Kekulé, as he said that the double bond, they do not have any fixed position, rather they keep on changing their position inside the ring, and there are two resonance forms that rapidly interconvert into each other, and there is rapid equilibrium found between these two forms. So sometimes here there will be double bond and sometimes there will be single bond. So because the bonds, they keep on changing their position, that's why these two ortho products are actually same. So that objection was answered by the Kekulé. And then, my dear students, when these two structures were proposed, the next concept was the resonance description of the benzene. And in resonance description of the benzene, there are so many resonance structure of a benzene you can see on Google, but the Kekulé structures and the Devers structures, they are the most acceptable and most famous structures of the benzene. These two are the Devers structures and Kekulé structures, and these three are the Devers structures. My dear students, these five are the resonance structures. The resonance structures are also called as the canonical forms or the contributing structures towards the finding actual structure of any molecule. My dear students, all the resonance structures, they have same shape, same position of all atoms, same number of bonds, same bonding electrons, but different pairing schemes of the electrons, due to which there are different arrangement of the bonds in that molecule. So all these, they are resonance forms. They are only the bookish structures, they are found in the books, but there is no actual existence of any of these resonance form. They are just proposed possible structures of the benzene. These two are the Kekulé structures and these three are the Devers structures. In Devers structures, you can see some longer bonds like between carbon 2 and 5, between carbon 3 and 6, between carbon 1 and 4. And these longer bonds, they make the benzene unstable, they are energetically unfavorable. So according to Devers structure, benzene is relatively unstable, but in actual we know that benzene is highly stable. Therefore, the Kekulé structures are the major contributing structures in finding the actual structure of the benzene, and 80% contribution to the actual structure goes to the Kekulé structures with the 40% each. And my dear students, in finding the actual structure of the benzene, there is 20% contribution of the Devers structures with 7% contribution of each structure of the Devers. And my dear students, then this structure was proposed, which is also called as the Robinson structure or resonance hybrid structure of the benzene. In all these resonance form, benzene is hexagonal. So the first common point is that the shape of the benzene should be hexagonal, but there is difference in the bonding arrangement. So that is why instead of showing the bonds in the ring, we show a circle in the benzene ring, which shows the movement of the 6 delocalized pi electrons. So this one is the structure which is resonance hybrid. It is closest to the actual structure, but it is not actual structure of the benzene, because still today, up till today, the actual structure of the benzene is unknown. After the resonance concept, now there was hybridization and molecular orbital treatment of the benzene, according to which all 6 carbon in the benzene are sp2 hybridized. If they are sp2 hybridized, every carbon will be having 3 sp2 hybrid orbitals and 1 unhybrid 2pz atomic orbital. My dear students, first of all, the 2 sp2 hybrid orbital of one carbon, they overlap with sp2 hybrid orbitals of other carbon atoms, and the sigma framework is formed in which the carbon atoms are joined together. Such kind of overlap between two sp2 hybrid orbitals, that is called as sp2 overlap. There are 6 sp2 overlap, so there will be 6 sigma mods between the carbon atoms in benzene. And each sp2 hybrid orbital of one carbon, it overlaps with 1s1 atomic orbital of the hydrogen. Such kind of overlap is called as sp2s overlap. It also results in the formation of the 6 sigma bonds, but these 6 sigma bonds will be formed between carbon and hydrogen atom. So in the sigma framework of the benzene, there are total 12 sigma bonds, 6 between carbon to carbon and 6 between carbon and hydrogen, and there are total 12 sigma bonds with 24 sigma electrons. And then, my dear students, every sp2 hybridized carbon has one unhybrid 2pz atomic orbital. These unhybrid orbitals, they always show parallel overlap, due to which the pi bonds are formed. Look at this p orbital very carefully. It has equal opportunity to show the parallel overlap in this direction with this p orbital and in this direction with this other p orbital. So it means one p orbital can have parallel overlap in two directions. So that is why it will have half overlap with this p and half overlap with this p. So half pi bond is formed here and half pi bond will be formed between these two p. In complete structure of the benzene, all the orbitals, atomic orbitals which are unhybrid 2pz atomic orbital, they show overlapping in the two directions. So that is why in all the between all the carbon atoms, half pi bond is formed, and there is no complete pi bond between any two carbon atom in the benzene, and that is shown by this resonance. And my dear students, when you will add all these half pi bonds, you will get 3 pi bonds. It means there are total 3 pi bonds in the benzene, but a complete pi bond is not formed between any two carbon atoms. Rather, the half resonating bond is formed between the carbon atoms. And due to these 3 pi bonds, there are 6 delocalized pi electrons that form a protective sheath around the benzene molecule. And this protective sheath of the delocalized pi electron, that makes the benzene highly stable. And my dear students, there are 12 sigma bonds, 3 pi bonds. Total bonds are 15 and total bonding electrons are 30, out of which 24 are sigma bonding electron and 6 are the pi delocalized bonding electron. At the end, the most modern technique, that was X-ray diffraction, was introduced, but it was difficult to have X-ray diffraction of the benzene because benzene is liquid. In its physical state, it is liquid, and X-ray diffraction is applied to the solids. So first of all, benzene was converted to its solid substituted product, and then X-ray diffraction was conducted, which showed that benzene is regular hexagonal. All carbons are sp2 hybridized. There is 1.5 bond between all carbon atoms, 1 sigma bond and half resonating pi bond, and the bond length between carbon to carbon, that is 1.440 angstrom, which is in between the single and double bond. It also confirms that this is neither the single bond nor the double bond, rather it is something in between the single and double bond. All the bond angles, they are 120 degree. All the carbon to hydrogen bond lengths, they are 1.39 angstrom. So the final conclusion is that benzene is regular hexagonal, and every corner of that hexagon has one carbon and one hydrogen atom. All carbons are sp2 hybridized. All carbon to carbon bond lengths are equal, and they are 1.40 angstrom. All carbon to hydrogen bond lengths are equal, they are 1.39 angstrom, and all the bond angles are 120 degree. In this way, the benzene is cyclic and regular hexagonal, and there is no possibility of the open chain or straight chain structure of the benzene, and the closest structure to the actual structure of the benzene is this Robinson's structure. So it was all about the structure of the benzene. I am very hopeful that this lecture will be very understandable for you people. In case you find any problem You can ask in the comment section. Till then, take care.